Oh, it moved it away. All right, so for Chapter 5, we're going to talk about standard deviation as a ruler, or I'll say the word metric a lot, of a normal model. Now, normal distribution, you've heard people talk about a bell curve and normal distribution. A lot of things in nature have a normal distribution. So the standard deviation, when you're comparing different values, the standard deviation lets us know it's a good measure of the spread from the center. It also tells us the whole collection of values and how much it varies. It's kind of, I like to use the word metric, but if the standard deviation is relatively high, then you have a pretty wide spread. If the standard deviation is if it's low, then you have a relatively narrow distribution. But the most common measure of variation is the standard deviation, and it really helps us to determine how to make predictions with the data that we have. So when we look at standard deviations, one thing that's kind of important is Z-scores. And I will give a brief thing about this. So like if I'm measuring how many tickets I sell on an airplane, and how many people actually keep their flight, that's a different measurement than the average weight of a person or the average height of a person. Those are all different numbers with all different units. But I can do a standard deviation and use that to find what we call a Z-score. Now what a Z-score does is it literally standardizes everything. A Z-score of 1 for weight distribution would be very similar from a probability perspective as a Z-score of 1 for measuring heights. So we're looking for Z-scores, and that helps us to make a prediction on probabilities, right? Because you get 80% of 80%, I mean, that doesn't change. 80% of somebody's weight, or 80% of the people will weigh this much, or 80% of the people will be this average height or close to it. That's all done and calculated through Z-scores. So now the formula for a Z-score is y minus y bar over S, which is the standard deviation. So standardized values don't have any units. Z-scores measure the distance of each data value from the mean in standard deviations. A negative Z-score tells us that the data is below the mean, and a positive Z-score tells us it's above the mean. Standardized values have been converted from their original units to the standardized statistical unit of standard deviations from the mean. Thus, we can compare values that are measured on different scales, different units, or different populations. It is hard to underestimate the power of the usefulness of standardized scores. You will calculate them in this course a countless number of times. This is basically what we're going to do the rest of the year. Okay?
What, Z-scores?
Z-scores and probabilities and distribution, Jess. So we're going to add or subtract a constant amount from each value that just adds or subtracts the same constant from the mean. This is true for the median and other measures of position as well. All right. In general, a constant to every data value adds the same constant to measures of center and percentiles, but leaves measures of the spread unchanged. In other words, let's say I'm measuring the height of people and everybody was wearing shoes. Then I realized, wait, we should have, for whatever practical purposes, we should have had people take off their shoes. So I can go in there and I could look at the data and say, let's subtract an inch because the soles of the shoes are about an inch from everybody. Well, if I do that to every person, there's the Z-scores, when you have standardized scores, that is usually unaffected because it's based on the spread from the mean. The mean will change. The mean will go down by 1 inch. But the Z-scores will remain the same, and that's what they're trying to tell you. But you do shift the data, basically. So the following histograms show a shift from men's actual weights to kilograms by subtracting 74 kilograms from each. So what they're saying is the distribution looks the same, but the numbers are different, okay? So if I take and if you look at the x-axis, they literally are just subtracting 74 kilograms from each. So when you do a measure of the spread, the box and whisker plot looks the same, and the histogram looks the same. So everything looks the same, except the numbers are different. Does that make sense? Okay. So what is the center of the two distributions, and what is the IQR? Well, because the numbers are different, the numbers will be different. Does that make sense? Your median value will be different, even though the distribution looks the same. Your IRQ, or your IQR, will...
Is that the range?
Yeah, it's the interquartile range. Will be... Your interquartile range will have a different value because the values are different. So we're basically rescaling data. So when you divide or multiply, well, not in that last case, but in other cases, we can rescale data. And when you multiply or divide data values by a constant value, all measures of the position, such as mean, median, and percentiles, and measures of spread, such as the range or interquartile range and standard deviation, are divided or multiplied by that same constant. Okay? So here's another example. Men's weight data in kilograms, and then we multiply it by 2.2. Because we're converting it from kilograms to pounds. Now on this one, it appears a little bit to be slightly different, but that's just because of the scaling, how we divvied up the classes. The distribution is very similar, so we would rescale the data is what we're calling it, okay? So what we're really doing is making an argument for standardizing things, okay, using Z-scores. So again, the centers would be different because it's skewed data, would be looking for the median. The median changes because the numbers change. And the range would change as well because we're basically multiplying everything by 2.2. So whatever your median is, you're probably just going to take that and multiply it by 2.2, and that will give you the new median. The range is going to be the range would be affected too. So standardizing the data in Z-score shifts the data by subtracting the mean and rescales the values by dividing by the standard deviation. So we're kind of using two of these two techniques to give us a Z-score. Now standardizing into Z-scores does not change the shape of the distribution. We saw that by looking at the graphs. Standardizing the Z-scores changes the center by making the mean 0. And that's just based on the formula. And then standardizing the Z-scores changes the spread by making the standard deviation 1. A Z-score gives us an indication of how unusual a value is because it tells us how far away it is from the mean. The data value that sits to the right of the mean has a Z-score, it says right at the mean is 0. And I'm going to show you a graph of that in a second. A Z-score of 1 means the data value is 1 standard deviation above the mean, and a Z-score of -1 means it's 1 standard deviation below the mean. How far from 0 does a Z-score have to be interesting or unusual? I'm going to jump ahead. It's usually 3. Plus or minus 3 is almost all, it's about 99.9% or 99.7% of most normal distributed data sets fall within plus or minus 3 standard deviations. That's the empirical rule. I'll tell you that later. So there is no universal standard, but the larger the Z-score, whether it's negative or positive, the more unusual it is. That means you're further away from the center. We often consider a Z-score greater than 2 or less than -2 to be roughly an indication of unusefulness. But every data set is different. So you just got to look at the practicality of the data set. What are you measuring and what are you trying to do with the data? Remember that a negative z-score tells you the data falls below the mean, and a positive z-score tells you that the data is above the mean. Pro tip, if you forget which order to subtract, use common sense. In other words, if I say that the average weight for a male in the United States is 175 pounds, and I get a question about, well, what's the probability of somebody weighing less than 155? And then I go to do the math and I have a positive z-score. Somewhere I screwed up, because 155 is less than 175. So my z-score should be negative because the value that I'm interested in is less than the mean. Does that make sense? And vice versa. How many men weigh over 200 pounds? Well, that's over the mean, which is 175. So I should have a positive z-score. And that formula is interesting because you're subtracting something, and sometimes when kids subtract stuff in their head, like if I say 175 minus, or I said that backwards. When I say 155 minus 175, we know the difference is 20, but sometimes kids forget to write down that it's a negative 20, and that negative 20 will be divided by the standard deviation based on the data set. And we'll do all this math, but these are the concepts. So then z-scores and the normal model. There is no universal standard for z-scores, but there is a model that shows up over and over in statistics. The model is called the normal model. It's often referred to as a bell-shaped curve because it kind of looks like a bell. Normal models are appropriate for distribution whose shapes are unimodal and roughly symmetric. These distributions provide a measure of how extreme a z-score is. The normal model for every possible combination of mean and standard deviation works. We write n of mu, comma, that's lowercase sigma, so to represent the normal model. So this is mu, which is going to be the mean, and this is the Greek letter sigma, which is like S, and that represents the standard deviation in a population, and we'll talk about that. To represent the normal model, the mean mu and the standard deviation sigma. We use Greek letters because this mean and standard deviation are not numerical summaries of data. They are part of the model. They don't come from the data. They are numbers that we use to help specify the data. And that's an interesting way to say that. These numbers are generated from standardizing data, is what they're saying. So if I'm measuring the height of men, I'm going to have values that represent the actual height of men. When I go to standardize the model, I'm going to do some things, and mu will equal one thing, and sigma will equal another thing, and we got to crank through it. But usually, rule of thumb is that the Greek letters are associated with the population that you're interested in, and the regular letters that we use are associated with the sample. And we'll talk more about that. Such numbers are called parameters in the model. That's another thing you'll hear Mr. Adams use that term a lot. What are the parameters? Which parameters are we interested in? That's just a fancy way of saying the variable represents what. If we're measuring height, the parameter could be h for height. But we always kind of change that to be an x or y value. Okay. So then z-scores are pretty easy. You just take the y value and you subtract the sample mean over the standard deviation. Why did they say Latin? Those are Greek words. Are written. Those are Greek letters. Anyways, that's funny. Such summaries are called statistics. So we'll talk about statistics. When we normalize data, oh, I see what they're saying now. We call the standardized value a z-score. So once we have standardized, we need only one model. Mu will almost always be 0, and the standard deviation will equal 1. And that's what we call a standard normal distribution. Don't use standard normal distributions or the normal model for just any data set, since standardizing does not change the shape of the distribution. So there are different models. We'll try to cover them. If your distribution is too narrow or too wide, this sort of thing doesn't work. So we're just going to focus on mostly normal things: height of people, weight of people, how many leaves are on a tree, how many trees are growing in a forest, sort of thing. When we use a normal model, we are assuming the distribution is normal. We cannot check this assumption in practice, so we check it. We check the following condition: nearly normal condition. The shape of the data's distribution is unimodal and symmetric. This condition can be checked with a histogram or a normal probability plot, which we'll cover later. Here's the rule on standard deviations. The normal model gives you an idea of the extreme value that we're focusing on. You can find these numbers precisely, but it's useful to begin with the simple rule that tells us a lot about the normal model. In a normal model, about 60% of the values will, or 68% of the values will fall within plus and minus 1 standard deviation. About 95% of the values will fall within 2 standard deviations, and as I said earlier, 99.7% of all values will fall within 3 standard deviations. And so this is the rule here. What they're saying is, here's the average. Now this is a normal model, so this represents the mean, which is 0, right? Because mathematically we're at the center. Okay? So if this was height, this would be the average height, right here at the peak of the bell. The top of the hill would be the average height. Well, some people are a little shorter, some people are a little taller. So 68% of the population would be between minus 1 standard deviation and plus 1 standard deviation. Okay? Now, 95% of the population will be between negative 2 standard deviations and positive 2. Now, for a normal distribution, 99.7% of the population would be within plus or minus 3 standard deviations. Now, generally, there are people that can exist height-wise outside of the 3 standard deviations, and you would kind of think of them as outliers. But for most practical purposes, maybe I'm a manufacturer of clothing or something like that, I could use this data and some information like how many people wear large shirts, how many people wear medium shirts, or whatever. Okay? So you always want to sketch out a picture. This is going to sound trivial, but every time we do one of these problems, you want to sketch the normal distribution. You'll want to label what the mean is. You'll want to label the value that they're telling you, and then you want to fill in all that stuff in addition to cranking through the math. You'll see that when I go over some examples with you guys. You can find normal percentiles by hand. So when a data value doesn't fall exactly between 1, 2, or 3 standard deviations from the mean, we could look it up in the back of your book where it says normal percentiles. I'll also show you how to calculate that on a calculator. I like to use the calculator as opposed to looking it up in the book, but there are some limitations to doing the calculator thing. Table Z provides us with normal percentiles. Now, when they say normal percentiles, those are probabilities that people will fall in that area under the curve. So the AP test provides a normal percentile table, table A, which is basically the same thing as what's in the book. So during the portions of the exam, you'll have access to that. It's not a bad idea to look up the tables and then check your calculator too and see where you're at. You can catch mistakes. In other words, if you only rely on your calculator and you hit the wrong button, it'll give you the wrong answer. But if you hit the right button, it'll give you an answer, and if you check the table of values and that matches your calculated answer on the calculator, then you can feel confident submitting that answer. So here's an example of finding normal percentiles. So table Z is in the standard normal table in the back of the book. We have to convert our data to ZScores to use it. the figure shows us the area to the left we have of the z-score. So now when you look at this, when I see 1.80, I go to the 1.8 and then I look for 0.00. That means it's going to be 1.800. Now if I had 1.801, I go to 1.8.01. Does that make sense? Or I'm sorry, it'd be 1.81. So if I put, in other words, if I'm doing some math and I get a z-score of 1.81, I'm going to go 1.8 plus 0.01, which would give me 1.81. Does that kind of make sense? Yeah. But because it's 1.80, this 0.9641, that means that the red area from this gate or fence all the way to the left is 96.41% of the values of the distribution, right? So if I had an average height for men, and then I asked a student, I said, what is your height? And they give me their height. And then I want to crank through the math. I would say you're in the 96th percentile of all men. And I would say that 96% of men are either shorter than you or equal to your height. Does that make sense? Okay. That's what you're going to be doing a lot of. Sometimes we start with areas and need to find the corresponding z-score or the original data value. In this particular case, we know that the value is 25%. If that is the scenario, we can find out how many standard deviations that is away from the mean, and then plug that into that same z-score formula and find out the actual value. So in this case, we go back to table Z, right? And we look it up. We go, oh, well, this is about 0.25. And so this is negative 0.6 and then 0.07. So the z-score would be negative 0.67. So the first quartile then would be at about 0.67 standard deviations from the mean. And then you could plug that into the formula and figure out the rest. So now, you could do this on calculators. I recommend that you have a Texas Instrument 83 or higher. I will go over how to plug this into the calculators. I already have videos on my YouTube channel that you guys can check out that show you how to do this. We could do either way, all right? I can find the area under the curve, left tail, right tail. There's a complement. By the way, how much area is under that bell-shaped curve? 100% of the data, right? So when you think about where I'm at, if I know the z-score here is 25%, what's the stuff in white under the curve? 75%, absolutely. So we'll use that to our advantage when we're using our calculators and using the book, the table of values in the book. Consequently, if this is 25% and that's a negative, what do you think the upper 25% would be if this is symmetrical?
It would just be positive 0.67.
Yeah, you got it. That's exactly what it would be, okay? That's how you do the tail test and all that stuff. So in order for all this stuff to work, you really do have to determine if the distribution is normal. And there's some qualifiers for that. Is your data set larger than 40 values? You want a larger data set. But more importantly, we can enter values into a calculator and just do a quick histogram. And that shape will either look like a bell or it won't. And then you do a little bit of math. You look at the mean. Where does the mean fall? Is it in the center? If the median and the mean are almost the same, then it's probably symmetrical for sure. But there's a bunch of tests, and we'll do that with some real data in a little bit. A more specialized graphical display is a normal probability plot. If it's roughly normal, a normal probability plot approximates a diagonal straight line. And we'll go through that. That's something I got to teach you, but we won't get into it today. But basically, here's some data. I'll teach you how to do it, but not today. Here's some data. It kind of is normal. And then when we do the probability plot, it will kind of look like a diagonal line. Okay? The more it looks like that line, the more normal the distribution is. Yes?
Will it always be an increase?
In this particular one, it should, yes. It's a good question. Now, if you look at this one, this is skewed data. See how the probability plot is kind of curved? See how that works? And we'll talk about how you do that. Basically, what you're doing is you're plotting the actual values versus the normal scores. And if it's a normal distribution, you'll have a straight line. If it curves, then the data's skewed. Don't use a normal model when the distribution is not unimodal and not symmetric. Normal distribution will not help you at all with this data set. There are things you could do with this data set, but this whole standard deviation mean thing is not going to work. The bottom line is it won't work because you're going to use this stuff for practical real world things. Very common problem in statistics is how many I'll give you one that's used every single day. Airlines overbook their flights. Okay? So if the airplane holds 300 people, they've got to figure out how many tickets to sell, and there's a probability that a couple people won't show. They just don't pull a number out of thin air. They do a lot of complicated statistics to know on that particular flight they're going to sell an extra 6 tickets. In other words, they'll book it for 306 people or 304. And they know the exact probability of how many people are going to miss the flight based on the data they collect. Does that make sense?
Yep.
So they have a normal distribution. On flight 1, 2 people miss. On flight 2, 3 people miss. On flight 4, 4 people miss. On flight 5, 0 people miss. And they take that data and they make a normal distribution. And they go, well, what probability do we feel comfortable with? And then they work backwards, do the Z-score, standardize it, and all that stuff. The story data can tell may be easier to understand after shifting and rescaling the data. Again, just a reminder, we can shift things left or right on the number line by adding or subtracting values. We can rescale the data by multiplying or dividing. Mathematically, it doesn't really change the shape of the distribution, but the values will change a little bit. And the values will be consistent. But when you standardize it, Z-scores are a very good way to tell how far away you are from the mean and the probability of you being included. 9 times out of 10 is what's the probability that 300 people will actually get on the plane. So if you look at that data and the probability of 300 people will get on the plane and it's like 92% probability, then you can go back and say, all right, well, I can overbook it. What's the probability of 303 people getting on the plane? And that changes the probability a little bit. Z-scores can identify unusual or surprising values among the data. The 68, 95, 99.7 rule can be useful. Rule of thumb. We use the 95 and 99.7 rule a lot. When I do research, I collect a ton of data. If you look on the posters on the wall, I collect a lot of data, and if I'm within 95%, plus or minus 5% error, I feel very comfortable with the data. Now, some would like it to be higher, but 95 is good. Well, I know that I have to fall within 2 standard deviations of the mean, right? So if I make a measurement for research, those values will vary a little bit. right? So if you look at, I did the research on the solar cells, and I measured voltages in one case. Well, the voltage isn't going to be the same. So I make a prediction about what I think the voltage is going to be. I run, 50 trials. If I could figure out that 95% of those trials are or 95% of those trials are within the tolerances, then I feel comfortable about the prediction. Okay. And then again, it's just 1, 2, 3 standard deviations. You have to think about this stuff. Normality is an assumption. We'll talk more about that as we look at real data. Is the mean very close to the median? Is the interquartile range close to their appropriate Z-scores? We saw that 25% is plus or minus 0.67 Z-scores. So if I look at the raw data and I look at the 25th percentile, and then I do the math and the Z-score is pretty close to 0.67, then it's probably normally distributed. Does that make sense? Okay. These are some AP tips that'll help you guys on the AP exam. This is the most important part for you guys. Probability rubrics usually have 3 requirements. You have to have the name, parameters, and calculations. Full credit can be earned like this. The normal, like you got to write this down. This has to be a habit. The normal is describing the distribution. Mu is an actual value, 110. Sigma is 25. X equals 140. Then you write down the probability of the Z-score being greater than 1.2, which is equal to 11.5%. Okay? Writing all that information down gets you credit. You can't just write down 11.5% is what they're saying. What's nice about that is if you make a simple mistake, they know that you just made a simple mistake. So you can get partial credit. In other words, if you accidentally wrote down 2.1 for the Z-score and you had a different percentage, the person reading that problem will go, oh, they just made a simple mistake. However, drawing and shading a curve is also a useful and sometimes requested task. I do it as a math teacher every time I do one of these problems. I draw it out. I make the little sketch. I shade in where it would be under the curve. I write down where the middle is. I write down what the Z-score is and the actual value, and you'll see this as we do some example problems. Your calculator will let you skip the step of finding the Z-score. Don't do that. You could plug in a value and it'll tell you the probability. I want you to crank through, find the Z-score, and then use the Z-score to find the probability. And that's it. Any questions for me? All right, that's all I got on that.